Okay, hello everybody. Welcome back to the second tutorial. So last time we looked over the basic hello world. Now it's fine if you didn't understand that, it's completely okay. Just don't worry about it. We're now gonna go over everything in more depth, and starting again from pretty simple stuff. So it should be fun, and it's a large learning curve, especially from something like Python, if that's where you're coming from. So do not worry once again if you didn't understand. Okay, so let me just create a new directory. Let me just copy main.asm to top2. Alright, so I have my previous file from last time. Now over here, let's try doing some basic addition and basic subtraction. Let's do some some common sort of math operators. So let's say we want to add 10 plus 5. Remember how I said you can let me just zoom in here. So you can take you can move something like 10 to the register A, and then move something like 20 to the register B, and then you can just do add A comma B, right? So that's like the sort of the process. So and then the next value, that means that now A equals 20. Just ignore the CSH command, not fine. But that's sort of the process that you go through. So over here, let's say move rax comma 10, move rbx comma 10. So these are two separate registers. Or let me do 15 to differentiate them. And now do add rax comma rbx. So what does this do? So it moves the value 10 into the A register. It moves the value 15 into the B register. Then it adds the value of rax to rbx. So now what should happen is rax should be 10 plus 15, which is equal to 25. It should be the sum of rax and rbx. So now rax should be 25. Now, printing numbers out, so how do we print out our rax is a bit of a complex task, which we can get to later, but for now, let's just use a simpler way of sort of seeing if our addition is working, which is, remember how we used a system call to exit our program? In the same way, we'll use the system call to exit the program. However, instead of exiting with the system called 0, let's exit with the let's exit the program with the value of rax. So what I'm gonna do here is move rdi comma rax. This means that now rdi has the value of rax, right? So now we should see that rdi has the value 25, and since this syscall looks at rax sys that is now 60, which is for exit, it exits the thing with the code of rdi, which is now 25, because we move the rax value into rdi. So if all goes well and we run this, we can see that it exited the program with a code of 25, which is our sum. So we can see that our sum is working. Alright, so let me go here on the other one. 1 second, sorry. CD documents, tutorials, tutorial 2, and now remember we use the same thing. So nasm dash fl64 main.asm. So now we do this. We have a binary object file. We do ld main.o-o main.main. Now obviously this doesn't print anything, but it should have exited with the code of 25. Now to see what the previous command exited the code of, we can do something like this. All this does is it checks what the last program exited with the code of, and it was 60. Huh. That's interesting. That shouldn't be happening. Oh, okay. This is obviously, this is really obvious here. So we move rax comma 60, and then we move rdi comma rax. So now what happens is rdi has a value 60. Since you just moved rax is 60, rax is no longer 25. So instead, what we'll do is move rdi comma rax before. So we add RAX, so now it's 25. Then we move RDI, comma RAX, which means we move the value of RAX, which is 25, to RDI, and then we move RAX to 60, which represents the exit code. It doesn't represent exit code, it represents the system call for exit. So now let's do the entire process again. ld main.o, and then /main echo $? And 25. We look at that, the sum worked. Now, in a similar way, we can use something like multiplication. So we have 10, 15. Let's just do multiply RDX, RDX. Oh, I'm sorry. So for multiply, rather than you putting two registers, so rather than you doing add RAX, RBX, it automatically uses RAX as the first number for the multiplication. So all you do is do multiply RBX. All this means is you multiply RAX, RBX, but it's just written as just multiply RBX. You don't actually specify that you multiply RAX, RBX, if that makes sense. So now if I run this, I do LD. So this should give 150 because it's 15 times 10. So /min echo $? And will you look at that? It gives out 150. Now, our next step is we probably want to create something. We probably want to create a file, so we don't have to. We want to create like a batch file or a make file to run it, so we don't have to manually, type it all out. In my case, I'm gonna quickly create a shell script. So nvim run.sh. Let me just do nasm-elf elf64 main.asm ld main.o-o main and /main. So all this does is it compiles the assembly file, it converts it to an executable, and then runs the executable. All we've been doing, but it's just now in a run file. I'm just doing this to give it run permissions. Now /run.sh, and well, it simplifies the process, so we don't have to manually go through the process of compiling, like writing the compile commands every time. Okay, let's look over the division operator. So divide works in a similar way to multiply, where you don't actually put divide RAX, RBX. You just put the register you wanted to divide with, and it automatically uses RAX as the primary register. So it divides RAX by RBX. Now remember, for this it only works with integers. Floats are a whole nother story. Right now all we're worried about is integers. So let's say I have 1000, and let's do 20. So this should give 50 if all goes well. So /run.sh echo $? 50. 1000 divided by 20 equals 50. Now let's delete this. Alright, now let's say you want to get the modulus operator. So you know how sometimes you can do something like 20 mod 8 equals 4, right? So that checks the remainder of 8 into 20. So 8 goes into 20 two times and then has a remainder of 4. So using the division operator, it also, so when you use the division operator, what also happens is it gives the value of the register RDX as the output for the modulus. So dividing by div RBX causes RAX to be the output, so equals to RAX. But also what it does behind the scenes is it assigns the value of the remainder from the div RBX to the register RDX. So RDX is going to be the mod operator, is going to be the remainder. So let's do an example, shall we? So 30 20. So 30 mod 20 should equals to 10, right? Or let's actually do something but like 50, which should also equals 10. So 50 mod 20 equals 10. So same way, since we know that once we divide it, the RDX gets assigned to the remainder, rather than moving RAX to RDI, we're gonna move RDX, which is the remainder. So now RDI will have the value of the remainder, and that will be the exit code, which should be 10. Let's see if this works. Echo dollar question mark 10. Will you look at that? So you can also use modulus with this. Oh, finally, one thing I forgot to cover is subtract, which is very similar to the addition operator, where you just do subtract RBX from RAX. And let me now just change this to RAX again. So, Jesus, what was that? RDI, RAX. Okay, so what should happen here is 50 minus 20 equals 30, and if we run this, 30. Boom. So over there we got a quick overview of all the different math operators, or the simple basic math operators you can do with assembly language. So this is how you add two numbers. And the crazy part is each of these are just one instruction, right? So in an actual computer, like a CPU is capable of handling up to like 2 billion instructions, modern CPUs, a second. So it runs like billions of these, which is why you might be thinking, oh, if each instruction does so little, then how do programs run so fast? Well, modern CPUs are able to calculate billions of instructions in 1 second. So each of these are one instruction, so just like adding two numbers will take 0.03 seconds, 0.303 divided by 2 billion seconds if the entire CPU was allocated to that one task. It's just to show you like how powerful modern CPUs are, and like how immensely fast they are. Alright, so that will be it for this tutorial, which is just basic math operators in assembly. Thank you.